Okay, so in previous section, we talked about double integrals, but the double integrals we talked about were over a rectangular region for both x and y then. Yeah, where the x ran between a and b, and the y was between c and d. So that set up a, like I said, a rectangular region that we were integrating over for our particular two-variable function. Well, the question then becomes, what if we have a non-rectangular region that we're going to integrate over? So, for example, what if we're going to integrate over a region, and this is just kind of hypothetical here. What if my region looked something like this? Okay, so where I am still going, x is going from a to b, but you can't really say the same for y. It's not between a fixed two values of y. And so that's what we're talking about. We're talking about more general regions where it's not necessarily just a rectangular shape. All right, and so what we're going to do is we're going to call this region, in this case, this book calls it a region D, that we're going to integrate over. Our two-variable function, double integrate over that. Okay, well, in this particular case, what we can do then to evaluate this particular region, double integral, is, like we said, the x runs between a and b, but then the y values are going in between these curves here. And so what we're going to set up is, well, we're going to call this one, the bottom one, the g1 function of x, and then the top one, the g2 function of x. And so we can say y goes between g1x and g2x. Yeah, so we can say y is a function of x, and then for the top and the bottom one. All right, and so then, oh, and this, for reasons we shall see later, the book calls this one the type 1 region, D. Okay, because there will be a type 2 also. All right, and so here's the story then. To evaluate this double integral, as long as if f is continuous, over or on a type 1 region D, such that D is, like we described here, and the book writes it this way, D equals the xy's coming from, the x's are between a and b, and the y's are between g1 and g2x. Just the way the book writes it, or how we can write that. So if we've got this setup, f is continuous on that region D, then we can evaluate our double integral over D for f of x, y, dA, as what it turns out you're going to do is you're going to integrate with respect to y first. So we're going to do dy, then dx, integrate with respect to y, and then with respect to x. And so the limits of the integration then would be, the first one, the inner one would be g1x to g2x. And then we can just do the x from a to b. Okay, so let's do one of those. Let's evaluate this one here. Double integral over region D. Function is x squared minus 2xy dA, where D equals x comma y. Okay, and so let's verify here that we do have a type 1 region, because x is going from 0 to 3, and the y goes from 0 to 6x minus 2, and so obviously y equals 0 is down here, but 6x minus 2x, well, if we graph, yeah, that's just a line. Y-intercept is 6, and slope is negative 2, so I think it's going to go, yeah, it's going to nicely go through 3 there, yeah. And so if we go from x is 0 to 3, y is, so we're talking about this region right here. So yeah, we want to, we can see that this is a type 1 because we're going, I guess it's a very simple bottom function here, y equals 0 is here, but then we're going to y equals 6x minus 2x here, and sometimes they drawing a line here. Yeah, we want to go, as far as y goes, I want to go from 0 down up to the 6 minus 2x line. So that's type 1. And so the way we evaluate it is we set it up, we do the integrate the y's first. And so this integral here what you've got to set up would be good to do the y's first, so dy and then dx. So what are our limits here? 0 to 6 minus 2x, and then the x is 0 to 3. So we evaluate that. Yeah, we have 0 to 3. This, first of all, would be with respect to y, integrate with respect to y. So that'd just be x squared y. X's are constants, and that would be y squared over 2, so the 2's will cancel, be just minus x, y squared, right? From 0 to 6 minus 2x. And then we'll integrate with respect to x once we do that. All right, and so these go in place of y's. And notice y is 0, it would just be 0, so that's good. So we have 0 to 3, x squared times 6 minus 2x minus x times 6 minus 2x squared. And I believe now we need to integrate that with respect to x, so I believe it would be easiest to go ahead and multiply all those out, right? 6x squared minus 2x cubed. This would be what? 36 minus 24x plus 4x squared, and so that would be minus 36x plus 24x squared minus 4x cubed if I distributed my minus x there. Check me if I'm right there. Look right? And so that is 0 to 3. We got minus 6x cubed minus 30, whoops, plus 18x squared minus 36x. And so we evaluate that. Is that right? Looks okay? I got something else. You got 30x squared? I believe you're right. Okay, so yeah, that's, I subtracted instead of added, so yeah. So it should be 30x squared. Just checking you. Okay. Okay. Could do that, yeah. I just leave it though, let's see, that'd be minus 6 over 4 x to the 4th plus 10x cubed minus 18x squared. 0 to 3. So that'd be too bad, that's 3 halves. So it'd be minus 3 halves times 3 to the 4th is 81 plus 10 times 27, so that'd be 270. Minus 18 times 9, and everything else is 0. And so, does that come out to be, what does that come out to be? Three halves, 81. 270 minus 18. 9. Yeah, make it 27 halves. Okay? All right. Look okay? Okay. Now, the others, since we talked about type 1 region, there must be other types, type 2, and there is. We also, for our double integral, could have D like this. Okay, so this one, in this case, it would not be wise, I guess we could say, to do it like we did, where we did, from this up to here, because, well, there's just a lot of different variations that would have for y, the function of y, because, in here it'd go between these two horizontal lines, and here it'd go between that curve itself, and so it makes more sense to do something with x as a function of y, right? So name these two functions, x equals, I think they call it h's. So this one, we usually do the left one first, so that'd be h1x, and this is h2x. And so integrate the first of all our double integral over region D, but do, first of all, the integral with respect to x, then with respect to y, do the other integral. And so that means, we're going to go x between h1 of x and h2 of x, and then y would go from c to d. And so if our region makes more sense, or would be easier integral to do this way for various reasons, we can do that. We have options, as they say. So this is the type 2 region D. Okay. All right, so let's look at one of these. Probably should use so let's evaluate our integral over region D. The double integral over region D, e dx over y dA, and d equals xy, such that y goes between 1 and 2, and the x is between y and y cubed. And so just from the setup alone, this is this is going to be easier. This is a type 2, easier to integrate with respect to x first than it is to integrate with respect to y, because if you look at region D here, y is going from 1 to 2. The x, all right, so we've got 2, we've got x equals y, and we've got x equals y cubed are the boundaries there, right? So y equals x is this. X equals y cubed is and so it makes more sense here to do first of all because we're going, this is the region we're talking about here, right? Do that region in there. So it does make sense to do with respect to x, because if we do it with respect to y, we've got a little mess there. Okay. All right, so our integral, double integral, region D, x over y dA. And this is also another consideration here. If you think about it, if I integrate this with respect to y first, if I integrate this with respect to y first, basically what I've got is, x is a constant, and so I've got e to the x times e to the 1 over y. So which one of those do I want to integrate first with respect to? E to the x, because that's a simple antiderivative, right? This is a little more complicated. Yeah, I mean, we could still do it. Still could do it. Anyway, okay. Actually, I don't think we could either. That's e to the y to the negative 1, and so we couldn't do substitution there. So anyway, I don't think we could do substitution, because you'd need a y to the negative 2 somewhere. But anyway, all right. But we don't have to. We know it's going to be first dx, then dy, so we're going to integrate with respect to x, then with respect to y, and so what have I got for my limits here? So doing it with respect to x, so the x goes from y to y cubed, and then the y goes from 1 to 2. Okay, so u equals x over y, and we're doing that with respect to x, so that would be 1 over y dx. Okay. So y du is my dx. All right, so there we go. Okay. Sorry, my bad. So that's 1 to 2. E to the u, and then y to u. Okay. So that would just be e to the u. Oops. E to the u times y, so that'd be y times e to the u, which is x over y. And then we're going to run that from y to y cubed. All right, so that would be integral 1 to 2. Is that okay? Sounds right? Okay. So that would be integral 1 to 2 of y times, and then, yeah, the x is the y cubed, so it would be e to the y squared, minus y times e to the first. Okay. Yeah, because the other one, the other way I did it, the incorrect way of doing it, I wasn't going to be able to do it. All right, so this again is, now I've got to integrate this with respect to y, and so yeah, now the way it comes out, this is doable. Because if we let u equals y squared, then du is y dy. And so yeah, that's just e to the u then. All right? Okay? And then that's 1/2 y squared times e. To y dy. Okay, thank you. So this would be 1/2. Thank you. Messing my u substitutions up. Of course, u is y squared, so let me just put that in so I can then evaluate that from 1 to 2. All right, so that's 1/2 e to the y is 2, so it'd be e to the 4, and minus 1/2 4e. And then plug in the 1, we have 1/2 e to the 1 minus 1/2 e. Ooh, those cancel out. And so we just are left with 1/2 e to the 4th minus 2e. Yep. Okay. Whew, I messed that one up.